In this lesson, we are going to discuss balancing chemical equations. At the end of this video lesson, you should be able to define the law of conservation of mass and apply the law of conservation of mass in balancing chemical equations. In chemical reactions, bonds are either broken or created to form new substances. This means that the substances in the reactant side of a chemical equation should never be present in the product side. In this reaction, the combustion of methane leads to the formation of carbon dioxide and water. There are three elements present in this reaction: carbon, hydrogen, and oxygen. If we are going to look closely at the composition of each substance in the reaction, we have one carbon atom on the reactant side and one carbon atom again on the product side. For hydrogen, we have 4 from the reactant side and 2 from the product side. Lastly, for oxygen, we have 2 from the reactant side and 3 from the product side. After comparing all the atoms from the reactant and product side, we can see that only carbon retained its number in the reaction. What about hydrogen and oxygen? Is it possible that there will be a loss of hydrogen atoms in this reaction? Or is it possible that there will be a gain of oxygen atoms in the reaction? As mentioned earlier, the bonds will either be broken or created to form new substances. So this means that if there are 4 hydrogen atoms in methane from the reactant side, there should also be 4 hydrogen atoms in the product side. Thus, there should be 2 moles of the water molecule. With this, the 4 hydrogen atoms from the reactant side will be equal to the 4 hydrogen atoms of the product side. Earlier, we had 2 oxygen atoms in the reactant side and 3 oxygen atoms in the product side. However, since we added another water molecule to have equal atoms of hydrogen, the oxygen count became more unequal. Now we have 2 from the reactant side and 4 from the product side. To have an equal count of oxygen, we can add 2 more oxygen atoms in the reactant side in the form of the diatomic oxygen molecule. Now, we have 4 oxygen atoms in the product side and 4 oxygen atoms in the reactant side. This means that for this reaction to proceed while maintaining the balance of elements, there should be 1 mole of methane for every 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. This reaction now follows what we call the law of conservation of mass. This law states that the matter cannot be created nor destroyed. It is only converted from one form to another. Each substance in the reaction would have a numerical coefficient indicating the number of molecules that is required to conserve the mass of the substances per number of atom. The most common way to follow the law of conservation of mass is to balance chemical reactions using the inspection method. In inspection method, we identify the elements present in the reaction and count the initial number of atoms representative for each element. Then, we do trial and error to adjust the number of atoms until we get an equal number of atoms in the reactant and product sides. Let us balance this reaction by inspection method. Here we have aluminum reacts with iron 2 nitride to form aluminum nitride and iron. The first step in inspection method is to list down all elements present in the reaction. These are aluminum, iron, and nitrogen. We are then going to compare the number of atoms in both the reactant and product side. The rules in counting the number of atoms in each side of the reaction is to take note of its subscript and multiplying it to its coefficient. If an element is present on one or more substances, we add the number of atoms for each substance. For aluminum, we have 1 on the reactant side, from the monoatomic reactant aluminum, and 1 on the product side from the ionic compound aluminum nitride. For iron, we have 3 on the reactant side from iron 2 nitride, and 1 on the product side from the monoatomic product iron. For nitrogen, we have 2 in the reactant side from iron 2 nitride, and 1 on the product side from aluminum nitride. We can see here that only aluminum is balanced. Since the inspection method is a trial and error method, there is no exact rule on what substance to adjust first. But a technique in balancing using inspection method is to balance the substance which is alone and or divisible by the number of the other side. Here, we can see that we can adjust either iron or nitrogen, but we need to consider which substance will be easier to be adjusted. For this reaction, we may adjust iron first because it stands alone. Since we have 3 from the reactant side and 1 from the product side, we need to adjust the lower number, which is 1 from the product side. Thus, we put 3 because 1 multiplied to 3 is 3. Thus, we have 3 atoms of iron in the product side. Now, we only have nitrogen unbalanced. Since we have fewer nitrogen atoms in the product side, we will adjust the product side. Thus, we have 2. This makes the number of nitrogen atoms in the product side 2 also. However, since we adjusted nitrogen in the product side, the aluminum count will also be affected. Now, we have 2 aluminum atoms in the product side. This makes it greater than the aluminum in the reactant side. Since aluminum in the reactant side is alone, we can easily write 2 as a coefficient. Let us now check if all elements have been balanced. For aluminum, we have 2 from the reactant side and 2 from the product side. For iron, we have 3 from the reactant side and 3 from the product side. And lastly, for nitrogen, we have 2 from the reactant side and 2 from the product side. Thus, our balance equation is 2 moles of aluminum reacts with 1 mole of iron 2 nitride to produce 2 moles of aluminum nitride and 3 moles of iron. Next, for this example, we have the reaction of potassium bromide and iron 3 hydroxide resulting to the formation of potassium hydroxide and iron 3 bromide. Again, the first step in inspection method is to identify the elements that are present in the reaction, and these are potassium, bromine, iron, oxygen, and hydrogen. We are going to compare the number of atoms for these elements in both the reactant and product side. What made this reaction different from the first example is that we have a substance that has a parenthesis within it, and that is iron 3 hydroxide. The same rules apply here, but the subscript of the parenthesis will be distributed to each element inside it. If the element inside it has a pre-existing subscript, we are going to multiply the subscript of the parenthesis to the subscript inside. Let's now count the elements. For potassium, we have 1 from the reactant side, particularly from potassium bromide, and 1 from the product side from potassium hydroxide. Bromine has 1 from the reactant side from potassium bromide, and 3 on the product side from iron 3 bromide. Iron has 1 from reactant side from iron 3 hydroxide, and 1 on the product side from iron 3 bromide. For oxygen, in the reactant side, it is found in the parenthesis with the subscript of 3. Thus, we multiply 3 to each subscript. This gives us 3 oxygen in the reactant side. For the product side, we have 1 oxygen in potassium hydroxide. Lastly, for hydrogen, since it is also in the parentheses, we have 3 from the reactant side. For the product side, we have 1 from potassium hydroxide. We can see here that only potassium and iron are balanced. But these are not yet final since they may be unbalanced as we adjust the coefficients of the other substances. Another technique in balancing equations is to balance oxygen and hydrogen lastly. This is because they are usually paired with other elements. So, it is better to balance the elements that are not oxygen and hydrogen. With this, we balance bromine first. Since the reactant side is lower than the product side, we will adjust the coefficient of potassium bromide in the reactant side. For 1 to be balanced with 3, we write 3 as a coefficient of potassium bromide. We now have 3 bromine atoms in the reactant side. This is now equal to the bromine atoms in the product side. However, since we adjusted potassium bromide, potassium becomes unbalanced. Between the reactant side and the product side is lower. Thus, we put 3 as a coefficient of potassium hydroxide. This gives us 3 potassium atoms in the product side. Since we changed the coefficient of potassium hydroxide, oxygen and hydrogen will be affected in the product side. Thus, we have 3 oxygen atoms and 3 hydrogen atoms. This is the advantage of balancing oxygen and hydrogen at the last part. It now seems that the elements are already balanced. But let us check if we have balanced the equations correctly. 3 moles of potassium bromide gives us 3 potassium atoms and 3 bromine atoms. 1 mole of iron 3 hydroxide gives us 1 iron atom, 3 oxygen atoms, and 3 hydrogen atoms. 3 moles of potassium hydroxide in the reactant side gives us 3 potassium atoms, 3 oxygen atoms, and 3 hydrogen atoms. And lastly, 1 mole of iron 3 bromide gives us 1 atom of iron and 3 atoms of bromine. Therefore, our coefficients are correct. Sometimes, the inspection method may make you balance an equation for a very long time, especially for those with huge subscripts. To account for this, another technique is used. This is called the algebraic method. We are going to use this equation to discuss the algebraic method. We have calcium phosphate reacts with silicon dioxide to produce tetraphosphorus dicoxide and calcium silicate. In doing the algebraic method, we are still going to identify the elements present in the reaction. These are calcium, phosphorus, oxygen, and silicon. The unique thing in this method is we will not be doing trial and error. Instead, we are going to use linear equations. Thus, we assign variables as coefficients. We will use A for calcium phosphate, B for silicon dioxide, C for tetraphosphorus dicoxide, and D for calcium silicate. We're going to identify the linear equations that will allow us to identify the actual values of the coefficients. To do this, we're going to get the sum of all products of the variables and subscripts per element per side. Let us do calcium first. In the reactant side, we only have one substance that contains calcium, and that is calcium phosphate. Thus, the left side of the equation is 3 times A or 3A. This will be equal to the calcium variable in the product side. This will be 1 times D or simply D. With this, calcium is represented as 3A is equal to D. For phosphorus, since it is inside a parenthesis, we multiply its subscript and the subscript of the parenthesis. Thus, we have 2 multiplied to 1, it will then be multiplied to A. Thus, the reactant side is equivalent to 2A. This will be equal to 4 times C or 4C in the product side. For oxygen, in the reactant side, it is present in 2 substances. For the first substance, which is calcium phosphate, 2 will be multiplied to 4 and then to A. Thus, we have 8A. It will be added to the product of 2 and B from silicon dioxide. Thus, for the reactant side, we have 8A plus 2B. The same case is present on the product side. Since there are 10 of oxygen in tetraphosphorus dicoxide, we have 10C. This is added to 3D of calcium silicate. In short, oxygen is represented by 8A plus 2B is equal to 10C plus 3D. Lastly, for silicon, we have 1 from silicon dioxide. Thus, we only have B. This is equal to D because there is only 1 from calcium silicate from the product side. And we're done with writing the 4 linear equations to get the coefficients of the substances. What we're going to do now is to get the values of each variable. We can let any variable be equal to 1, but it will be of big help if we assign it to the simplest variable. In this case, it's either B or D, because for silicon, we only have 1 on each side of the equation. But for this, let us assign 1 to B. Since B is equal to D, D will also be equal to 1. Now, we can solve for the other variables. We will select the equation with the most number of known variables. Calcium has 1 known and 1 unknown variable. Phosphorus has no known variable. And oxygen has 2 known and 2 unknown variables. Therefore, we should get the value from A from calcium first. We are going to use 3A is equal to D and substitute D with 1 because it is already solved. To get the value for A, we divide both sides of the equation by 3. Thus, A is equal to 1/3. So far, we have A is equal to 1/3, B is equal to 1, and D is equal to 1. It will be easier for us if we omit any fractions. So what we're going to do is to multiply all known variables by the denominator of the fraction. In this case, it is 3. So if we multiply 3 to all variables, we're going to have A is equal to 1, B is equal to 3, and D is equal to 3. We are now only left with C. So we are going to use either the equation for phosphorus or oxygen. But since the formula for phosphorus is shorter, this is what we're going to use. So we have 2A is equal to 4C. Substituting 1 for A, we have 2 is equal to 4C. To get the value for C, we divide both sides of the equation by 4. Thus, we have C is equal to 1/2. Since we have another fraction, we need to omit it again. Thus, we multiply all variables to the denominator of the fraction. Thus, we have A is equal to 2, B is equal to 6, C is equal to 1, and D is equal to 6. Since we have already completed the variables, we can now substitute the temporary coefficients with the values and check if the elements are balanced already. We are going to compare again the elements in the reactants and the products. Let us start with the first substance, calcium phosphate. Calcium and calcium phosphate has a subscript of 3. This will be multiplied to the coefficient 2. Thus, calcium in the reactant side is 6. Phosphorus in the substance has a subscript of 1. But since it is inside the parenthesis, we will need to consider the subscript outside, which is 2. Thus, 1 multiplied to 2 is 2. This product will then be multiplied to the coefficient 2. Thus, 2 multiplied to 2 is 4 phosphorus atoms on the reactant side. The same substance will give us oxygen with a subscript of 4 and will be multiplied to 2. 8 will then be multiplied to the coefficient 2, giving us 16 oxygen atoms. For the next substance, silicon dioxide, silicon has a subscript of 1 that will be multiplied to the coefficient of 6. Thus, 6 silicon atoms on the reactant side. The same substance will give us oxygen again, particularly 2 oxygen atoms multiplied to the coefficient 6. Thus, 12 will be added to the first 16 oxygen atoms, giving us a total of 28 oxygen atoms on the reactant side. Since we are done with the reactant side, let us now count the atoms on the product side. The first substance, tetraphosphorus dicoxide, having a coefficient of 1, will give us 4 oxygen atoms. The same substance will give us 10 oxygen atoms. Lastly, calcium silicate, having a coefficient of 6, will give us 6 calcium atoms. It will also give us 6 silicon atoms. Lastly, 3 oxygen atoms multiplied to the coefficient will give us 18 that will be added to the first 10 oxygen atoms. Thus, we have 28 oxygen atoms all in all in the product side. Comparing the counts of each side, the equation is said to be balanced. The final balance equation is 2 moles of calcium phosphate reacts with 6 moles of silicon dioxide to produce 1 mole of tetraphosphorus dicoxide and 6 moles of calcium silicate. Let us look at the second and last example for the algebraic method. Here we have the combustion of decane as represented by the reaction of decane and oxygen, producing carbon dioxide and water. Again, the first step is to assign the coefficients for each substance. Next is to identify all elements present in the reaction. We have carbon, hydrogen, and oxygen. The next step is to write the equations for the following elements. For carbon, we have 10 carbon atoms on substance A, thus 10A. This is equal to 1 carbon atom on substance C in the product side. Thus, we write C. For hydrogen, we have 22 atoms on substance A. Thus, we have 22A. This is equal to 2 atoms on the product side on substance D. Thus, 2D. Lastly, for oxygen, we have 2 atoms of oxygen on substance B on the reactant side. This is equal to 2 atoms on substance C plus 1 atom on substance D. Thus, we have 2B is equal to 2C plus D. We are going to assign 1 to any variable, but as much as possible, to the variable which could easily give us the values for the other variables. So let us assign 1 to A. If A is equal to 1, we can get the value of C by using the equation for carbon. 10A is equal to C will become 10 times 1 is equal to C as we substitute A with 1. Thus, we have C is equal to 10. Also, by using A, we could get the value for D. We are going to use the equation for hydrogen, which is 22A is equal to 2D. Substituting 1 to A, we have 22 is equal to 2D. To get the value of D, we divide both sides of the equation by 2. Thus, D is equal to 11. Since we now have the values for C and D, we can already use the equation for oxygen to get the value for C. We are going to substitute C and D with 10 and 11 respectively. This will become 2B is equal to 31. To get B, we divide both sides of the equation by 2. Thus, B is equal to 31 over 2. Since we cannot have a fractional coefficient, we will multiply all coefficients by the denominator, which is 2. Thus, we have A is equal to 2, B is equal to 31, C is equal to 20, and D is equal to 22. Now, we can replace all letter coefficients with their actual values. In substance A or decane, carbon has 10 initial carbon atoms. Multiply to the coefficient 2, thus 20 carbon atoms on the reactant side. The same compound will give 22 hydrogen atoms multiplied to 2, thus 44 hydrogen atoms on the reactant side. Lastly, substance B or oxygen gives us 2 atoms multiplied to the coefficient 31, thus 62 oxygen atoms in the reactant side. For the product side, compound C or carbon dioxide gives us 20 carbon atoms. It will also give us 2 oxygen atoms multiplied to the coefficient 20, resulting to 40 oxygen atoms. Lastly, water or dihydrogen monoxide gives us 44 hydrogen atoms, and 22 additional oxygen atoms for a total of 62 oxygen atoms. With this element counts, we therefore conclude that the equation is balanced. So there we have it. We have discussed 2 methods in balancing chemical equations. Specifically, we discussed the following concepts. The law of conservation of mass in chemical reactions states that matter is neither created nor destroyed. The inspection method of balancing chemical equations involves trial and error manipulation of coefficients. And lastly, the algebraic method of balancing chemical equations involves the use of linear equations to determine the coefficients. And this ends our discussion on balancing chemical equations.